In this series, we explore big data, obviously starting with the definition of what big data is. Now, I think that the easiest way to sort of really understand big data is to look at traditional data and its management. So, what is traditional data? Well, firstly, the vast majority of traditional data that organizations and governments and the like gathered was relational data. So, here we're talking about neat rows and columns. We're thinking about traditional, like let's say spreadsheet format data, or for those of you know what these are, OLAP cubes. But I mean, really, we're talking here about data that is structured very neatly. It's usually mostly quantitative data. If you did have qualitative data, it would still be, forced into these neat rows and columns. So things like someone's gender, male, female, etc., would be words, but it's still really just data. Um, and then traditional data management. So very importantly, firstly, that collected data are static and retrospective, meaning that collection had been done in the past and the data was stored previously and generally wouldn't change during your analysis. So the entire data set would be stored on one computing node. So in other words, we're talking about, onto a hard disk, a drive, a server, etc. The data could be processed using conventional processing power. And then traditionally, the data would be stored on disk, retrieved later, and analyzed. And then finally, very importantly, that the data could and would be analyzed using conventional traditional statistics, so ranging from means to regressions or whatever, but your typical traditional stats. Now, if that's traditional data, what is big data? And really, for me, big data is any data that by virtue of its characteristics, and we'll go through the characteristics next, cannot be treated in the traditional manner regarding collection, storage, processing, or analysis. In other words, any reason that you've got data out there that breaks the traditional way that you do things, it becomes big data. Now, what are these characteristics that typically break the rules of traditional data? And we talk about the 3V model, and I will expand on this a little bit, but there are traditional 3Vs. I think it was Gartner that came up with this, that forms a reason to call it big, to become big data, that breaks the original traditional rules. The first is volume. Now this is the traditional kind of big data. This is where this word comes from, big data. So we do in some organizations, in some situations, capture enormous data sets these days. Internet of Things can produce these absolutely amazingly huge streams of data. Some scientific endeavors produce ridiculous amounts of data, and ultimately that breaks the rules. Why does it break the rules? Because A, you can't store it on one node anymore, it's too big. You need to split it up across many different computers, it doesn't fit on one drive. You can't analyze it using conventional processing power, nor would you be able to, because processors, are then attached to specific nodes, and so on and so forth. So large data sets is certainly one reason. Interestingly, though, it's not really the focus anymore. We've kind of solved this one, and I will go through later through some of the ways in which we've solved this one. But we have solved this one mostly. There are two other very interesting reasons why the traditional rules might break. So the second is velocity. And velocity actually is speaking to data that is both potentially produced very rapidly, very fast, but more importantly, that you actually have to analyze very fast. So this can be actually very small packets of data. It doesn't have to be high volume data. But by virtue of the fact that you need to analyze it potentially as it's being produced, or very, very quickly as it enters your computing environment, that breaks the traditional rules. Remember, traditional data, we would store it to disk, retrieve it later, then analyze it. Now, with velocity problems, you often can't do that. You don't have the luxury. Now, to look at velocity a little bit more, with some realistic world examples, I think the poster child for velocity is fraud analysis. So with fraud analysis, you've got a credit card swipe, and maybe you're overseas in Istanbul buying a leather jacket. You swipe your card, and of course, what you all know is that very quickly that data travels, halfway across the world potentially back home through multiple banking networks. So we also discussed this under IoT, by the way, this whole thing. It arrives at your bank. Your bank needs to take that credit card swipe, which is a very small packet of data, and analyze it very quickly for signs of potential fraud, for signs that they weren't expecting you to be in Istanbul, or it's an unusual amount of money in an unusual currency, or maybe an unusual time of day, something like that. So they've got various rules for how they do this, and those algorithms are crucial. But the problem is both it's both a hardware problem. You can't, where do you analyze it? You can't afford to bring it into hard drive, maybe into your data warehouse and then only extract it 3 o'clock tomorrow morning. It can't happen like that. Another poster child is streaming data that comes out of IoT sensors. So the Internet of Things, we talk about using sensors that are censoring various things, and sometimes that's a velocity problem. For example, you have sensors on machinery in a factory that are monitoring the machinery for signs of breakdown or problems. The algorithms need to be able to take that data as it's produced and then act on it. So there's various examples. Again, it doesn't have to be high volume at all. But the real game in big data is variety, the third V. Now, variety refers to the fact that, in fact, all the way through human history, always, there was a lot of data out there that, we didn't even used to class it as data. It was really classed as information, documents, tapes, live streaming broadcast. All of this stuff, which is pictorial, it's text, it's speech, it is data. It has data qualities. It's full of information, and we could never analyze it, not on any meaningful level. And really only recently have we figured out that that this could be treated as data. Now, we call this unstructured data, data that's not structured in the traditional relational database. And it ticks a lot of these different boxes. It can be very big in volume. Often you do need to analyze it quite fast. Let's say, for example, speech recognition, you need to be able to analyze it as the person is talking very often. And finally, it's not traditional relational data. You can't apply traditional statistics to it, and there are a whole different set of rules. Now, this to spoil. To put a bit of a spoiler on one of the later sections in this chapter, this is the real playground of artificial intelligence, is to take unstructured data and understand it. So that really was the big solution here. Now, these three are the big three. Any one of these three can make it a big data problem. There are a couple of others to consider. So veracity, so data where by its nature, for example, there's a lot of ill-matched or inaccurate data. The sheer volume itself makes this a problem. So just for example here, as people's digital identities out in the world, spread with even for one person with a lot of diversity. You might have a work email that gets used in some situations, or a work identity, but you might be a lady who has gone the traditional route of taking on a married name, so you might have be in some databases under the married name rather than the maiden name, and you might have your Google address there rather than your work address, and then you might have social media handles, like you might be Fluffy Slippers 321 somewhere in Instagram or whatever. I mean, that's one example here where the problems of figuring out that actually these different identities, this is one person. These are big problems. Another interesting one is variability. So here we talk about peaks and troughs in data, and we do see large peaks and troughs. And this presents a particular problem because very often the kind of processing and computing that deals with the data can't deal, especially with very high peaks. The poster child for this would be like Black Friday and its effect on retail websites. We've often seen large retailers just simply shutting down during Black Friday rushes on their websites because they just can't handle the load. Now, we talked about this actually under cloud computing, right? Where we talked about the Elastic Cloud and how Elastic Cloud can, if it's done really well, help with this problem. So this is also a solution that is becoming better. And then just value, and really the point here is that there can be very large value accruing from big data. And that value, in other words, value that can stem from understanding customers better or having better processes, etc., really does drive the need to have good solutions for big data. We do pick up on that point later. So this is an introduction to big data. What is it? It's data that by any virtue of any characteristic, whether it's volume, whether it's variety, whether it's velocity, whether it's because you have high peaks, whether it's because it's very messy, any of these can break the traditional rules and make the people who deal with it require new solutions, and that's the key thing here.